Good afternoon, everybody. I'm pleased to have the opportunity to share with you the results of some of the experiments that I and my research group have run over the past few years, examining kinetic isotope effects specifically during electrochemistry or redox processes. So I'd like to start off by telling you a little bit about why a geophysicist might want to do electrochemistry. But let's start first with just a quick definition. What is electrochemistry? Electrochemistry is a chemical reaction in which a charge, mostly an electron, but sometimes a proton, is transferred from one species towards another. That's part one of the definition. It would be trivial because if you look in detail about chemical reactions, they often involve movement in electron density from one species to another. And I see Jean-Alexis nodding his head right now. The key is with electrochemistry is that electron jump is the rate-limiting step in the multiple process that defines the chemistry. And so that is if you provide a reservoir of electrons, for example, on a reactant side, it will push it towards the product side. Or if you provide a sink of electrons or an abundance of holes, it will drive the reaction rates forward and backwards. So as an example, I'm showing you a redox reaction between iron, which oxidizes to form a ferrous iron and liberates 2 electrons. And one of the keys of electrochemistry is you have to maintain charge balance, of course, in all chemistry. And so that electron now has to be taken up by a corresponding reduction reaction. In this case, I've given you 2 options, and these are the 2 options that are the most in almost all aqueous systems that we're familiar with at the surface of the Earth. There are 2 reduction reactions that will take place when you, for example, corrode iron metal. If the water is open to oxygen, the reduction will be oxygen. So you'll have oxygen, partial pressure of 0.2 in equilibrium in the water, will take up those 2 electrons and become an oxygen ion. Or if the environment is deoxygenated, so for example, if it's in a crevice, like a crevice corrosion, and the oxygen has already been reduced, then you'll move to much lower potentials and you'll reduce the water itself. You'll hydrolyze the water, and so the hydrogen ions will take up the electrons and become H2. So these are the reactions that will happen, for example, in a neutral in a more acidic environment. If it's neutral, we have to add the hydroxyl ions. So there's an oxidation reaction and a reduction reaction. So this is what an electrochemical reaction looks like. And the reactions that I will be talking about are these types of reactions. They're aqueous reactions, not necessarily the reactions that might take place between a silicate and an oxide, for example, and a metal reservoir, although the same types of rules apply to those systems. We can understand electrochemistry the same way we understand chemistry. That is, we can do the thermodynamics when we take into account the activity of the electron. So we can talk about the thermodynamics, the driving force, the free energy driving force for this reaction. When it's an electrochemical reaction, we can define this free energy in terms of an equivalent voltage. Okay? And the equivalence we'll see later is related to Faraday's constant, which talks about the number of moles of electrons that are transferred in a reaction. And so 1 volt of electrochemical potential for this type of reaction is equivalent to 2 times Faraday's number, which is approximately 200 kilojoules per mole. So if you're used to thinking about chemical joules per mole, this is typical bond-breaking type of reaction energies, and that's equivalent to about 1 volt. So just like when we consider thermodynamics, we often have to consider kinetics, how fast a reaction happens. So thermodynamics will tell us whether or not a reaction is energetically favorable. We have to consider kinetics to let us know how fast that reaction might take place. And so in electrochemistry, the kinetics of this reaction is a reaction rate. And so we can measure the amount of product produced as a function of time, and that gives us a rate. But when electrons are being transferred, we can also measure simply that electron transfer, and so that gives us a current. So we have our thermodynamics and kinetics, our energies for driving force for reactions, and our reaction rates now framed in terms of something that we can start to handle really easily in the laboratory. Volts and currents, we can supply them, we can measure them, and they're also extremely powerful in driving reactions. They're efficient energy sources, electrochemical energy sources. So those are definitions and some terminology. In the Earth, electrochemical processes are ubiquitous, from the formation of the core from the mantle. So we've talked about whether the core will take up metals and which ones prefer to go into the metal versus stay oxidized in the mantle. And indeed, that's why this geophysicist became interested in electrochemical reactions, was looking at those reactions at the core mantle boundary. Whole Earth volatile cycles involving elements like carbon or sulfur or protons, which is my way of referring to water, involve redox reactions. So when are these elements in their oxidized states? When are they in their reduced states? Who do they give their electrons to? And who in the Earth is there to take the electrons? So broader than just oxygen. Okay, and notice that oxygen is not a player in my volatile cycle in the deep Earth, in that list. Broader than that, the question becomes who gives the oxygen, or who gives the electrons and who takes the electrons. And that, of course, is dependent on some deep Earth definition of where each of these species are in an electrochemical series. There are other important applications, including precipitation and dissolution when there's oxidation involved, changing of iron +2 to iron +3 in an oxidized environment, weathering reactions, mineral resource and recovery, and of course cleanups of the messes that we make when we recover ores and minerals. So there's lots of reasons why electrochemical processes, a lot of places in the Earth, from the atmosphere to the core to planetary formation processes, where electrochemical processes are important. In the laboratory, as I alluded to before, we have really good control of electrochemical equilibrium and disequilibrium. And we can measure the rates relatively easily by measuring currents. We have very sensitive methods to apply electrochemical disequilibria without changing the chemistry. And then measuring the rates of reaction with very high precision by measuring the currents. So the electrical power is extremely efficient at driving chemical reactions, and then small inputs, like a millivolt, will have relatively large effects of tens of hundreds of joules to kilojoules. And then finally, the reason that electrochemistry is nice to play with is that the thermodynamics are extremely well understood and have been explored in great detail, and even the kinetics of simple electrochemical processes are well understood. So we have a way to actually have a predictive theory to describe electrochemical processes. So if there are redox processes involved in some of the tracers that we might use to look at processes in the Earth, as Anat was talking about before, then with electrochemistry we have a hope of really pinning down those mechanisms in some exact ways. So a predictive theory is possible. So the question that we set out to address, the original question was, if there were reactions at the core mantle boundary, would we be able to tell? But it's very difficult to do an experiment in isotope fractionation at the high pressures and temperatures that are relevant to core mantle boundary. So we backed off and asked the same question, but in a simpler way, which is, do redox processes or electrochemical processes generate specific geochemical signatures so that we might be able to take a sample downstream and interrogate its geochemistry and say, aha, redox happened up yonder. That's the goal, that's the hope. So if that's the case, then perhaps we have some observable that has a signature at equilibrium, and then as we drive away from equilibrium, as our rates go higher, that the signature changes. So not only does it tell us that electrochemistry happened, but tells us exactly the driving force for that electrochemistry. So that's the hope of an electrochemical kinetic tracer. So Anat gave a beautiful introduction this morning to stable isotopes, and so I'll reproduce a little bit of the story here, because we will look to stable isotopes and some of these newer non-traditional stable isotope systems as potential markers for electrochemical processes. So what I've done here is I've shown again the elements with multiple stable isotopes that can be our stable isotope geochemical markers. And I've also highlighted in red those elements that also have multiple oxidation states. So each... oh, I've missed some. Yeah, sorry. Yeah, thank you. So also uranium. And there might be others down there that you see I ended up here at the third row transition metal. Sorry about that. But yes, there are other ones too. But where those elements are both multiple oxidation states and multiple isotopes, they will hold out the promise of generating specific isotopic signatures should they exist. So this is kind of our zoology of stable isotopes. So let's talk about how we can ask that question. So as you know, if you're an experimentalist, or pretty much in many endeavors, you can choose 2 out of 3, cheap, good, or fast. And so here were originally designed to be relatively quick and dirty experiments that were just to ask this, very general question, which is, are there stable isotope signatures that are associated with the rates of electrochemical reactions? So the experiment looks like this. This is a schematic of an electrochemical cell where we have our working electrode here. So we've got an electrode here. And then we have a counter electrode separated in an anode. And they're separated by a salt bridge so that I don't have mixing between these reservoirs where the reduction will be taking place and where the oxygen will be taking place. In an electrochemical setup, we also have a third cell which is our reference electrode, which is as close as possible to our working electrode. And that allows us, it gives us a 3-electrode system that allows us to simultaneously either control current while measuring potential or control potential while measuring current. And we use it in the second sense. We control our potential. We use it as a potentiostat while measuring current. And we run an electroplating reaction in which we fill a solution, which is about the size of our coffee mugs, with a salt solution, supported electrolyte, and then electroplate a very, very small amount of metal. So for example, in some of the reactions we'll see, I think this picture is maybe, I actually don't remember if that's iron or zinc, but a small amount of iron +2 in solution will be electroplated on the electrode. We'll pull it out of solution and then do a measurement. Well, the nice thing about the potentiostat is we have really good control. We can control chemistry separately by changing our mixture in the bath. We can control the voltage, right, the driving force at which we plate, which is also controlling the rate because they're tied together in the kinetics of electrochemical processes. We can choose how long we let it sit, so how much material is plated in the end and how much we evolve the reservoir. And in most cases, we just take a very small amount of the solution so that solution effectively remains an unevolved reservoir. So we're just taking a small amount out. We can look at that later. We can change the chemistry. We can do this in a controlled temperature environment. And then in the end, you can see we can also control the mixing pretty closely. So we could look at the mass transport to the electrode. Okay, and then we take that material, and then we Anat ran the first experiments at UCLA, so your results are highlighted first of all, because Anat was one of the developers of the applications of these high-resolution mass spectrometry techniques. And really, I mean, this was 10 years ago, almost exactly, a couple more years, right? It was 2004. And so we've run a series of experiments. I've run a series of experiments with different geochemists who specialize in looking at some of these different stable isotopes. And so here's a list of some of the collaborators, and we'll see some of the data that were generated in these collaborations. They're very fun experiments. Okay, so next I'd like to show some of the experimental results. And there's some things that we see in all of the experiments, including some of the mysteries that line up. So now what we've done is we've plated out some material, and we're going to take that material and we're going to scrape it off. We're going to collaborate with a geochemist who's an expert in making a high precision measurement of the composition of the isotope, the isotopic composition of what's been plated with respect to the original solution. So, not discussed some of the standards that people use, and of course we had to use standards while we were making these measurements, but in all of these plots I will show the isotope composition in per mil. So this is a part per thousand. These are negatives. They're always light isotopes that are electroplated. And I'm always showing it with respect to my starting solution. Okay, so I'm not with respect to a global standard, but with respect to my own internal standard. And that's actually one of the joys of experiments, is that it's a precise measurement yields precise results. So in all cases, we observe light isotopes that are preferentially electroplated, and are not reminded us that that is because it's a kinetic effect, that we're looking at a kinetic effect. And it will be related to the ratio of masses. So when we do our definition with respect to the heavy mass, these mean that the negative values mean that it's light. These numbers, 3.0, have been multiplied by 1,000. So you're looking at a 0.3% effect, which is actually huge for iron isotopes, as we saw in some of the data before. But if we include some of the larger biological variations in iron isotopes, the range of our natural potentials are here. The range of our observed isotope fractionations in nature are here. And then in terms of chemical processes, like biochemical processes, you can ask, what's the electrical potential or what's the voltage across a cell membrane? And these are on the order of a couple hundred millivolts. And so you're looking at a range of natural potentials that are similar to the types of potentials that we're applying in these experiments. The results we get show that close to equilibrium, we have very little fractionation. This was the first set of results. And then as we increase the driving force, which is also simultaneously increasing the rate, we get larger and larger fractionation values, always increasing to the negative. So the first answer is, yay, we did it. And it was very exciting. We are duplicating in the laboratory the breadth of what's observed in nature, not necessarily the same cause. But we can dial in an isotope fractionation by changing the voltage on our potentiostat. And this is nice. It could be a powerful tool to separate isotopes if we understood how it works. Okay, so these are our first three observations, and we've done several sets of experiments since then. The next set of experiment that we did was a stunner. So here's our first set. We're going to look at what we thought was a duplication, and we get this result. So again, here's our stock solution. Here's our isotope fractionation, always light. This is equilibrium. And now here we're driving the reaction forward. Each of these is a series of measurements, that we perform. We take the electrode out and scrape it off. So a couple of things to see. One, we've changed the chemistry a little bit. We've changed some other things actually, it was mostly the chemistry in this case. We've changed the chemistry of the starting solution. We still have low fractionations, but in this case, the larger fractionations are closer to equilibrium, and they evolve upward. In fact, all of the rest of the examples that you see are this direction. Some other things, fractionation is independent of time. So one of the things that we tested in these next series of experiments is we can run duplicate experiments, but now at the same potential, but holding the electrode in there first for amount of time so that it deposits 5 coulombs, then 20 coulombs, then 50 coulombs. This is equivalent to about 0.1% of that total reservoir being reduced to 1% of that total reservoir being reproduced. In time, this is on the order of a few minutes. This is on the order of a few tens of minutes. So it all scales. So those are the times that are associated with these reactions. We get the same result. Okay, so our fractionation results are rate dependent, but not time dependent. And that's nice. We're not dealing with transients in these experiments. So that helps us. Or if we are, the transients are on timescales that are either far shorter or far longer than our laboratory timescales. Yes, so in all of the reactions that I'm showing in this talk, I don't drain the reservoir. I did a series of experiments in which we did attempt to drain the reservoir. We evolve the deposition, we remove our electrodes as a function of time, and we keep measuring the stock solution, and we evolve up an Rayleigh fractionation pattern. In the end, we do a fit to a fractionation factor that is it's approximately the same as what we get when we do that end member. So we've run that experiment, and I could show those results at the end. Good question. Any other questions before we move to the next mystery? Okay, so as we change the bulk solution chemistry, one big example is the pH. That affects the magnitude of the isotope signature. So this was the data that we saw before. Now we were at 0.3% fractionation. This is zinc, by the way. So we've changed. I'm looking at a different system. So we see the same thing now in zinc that we did in iron. This is zinc chloride being deposited. We get these large isotope fractionations. They evolve upward as we change the driving force. Now, if we use acidified zinc sulfate, so the species of zinc in the solution is probably different in this case from this case, we get much, much larger isotope fractionations. In fact, zinc is even heavier than iron. So the fact that we're getting 5 per mil or 0.5% fractionations is huge. We are the record holders, as far as I know, for single pass fractionation for zinc. It's interesting in different ways that we might get into towards the end of the talk. The other thing that happens that you can see is we can run these experiments again at different temperatures. So these yellow symbols correspond to room temperature, and they're held at room temperature. And remember, Anat was very clear that isotope fractionation, at least the equilibrium isotope fractionation, is extremely temperature dependent. In fact, the more kinetic energy, the higher the temperature, the less isotopes seem to care about which state they're in. So equilibrium isotope fractionation predicts that the isotope fractionation decreases strongly as temperature squared. But you can see something really interesting here, which is as we go from 0 degrees to 25 to 50 degrees, so if we warm up our experiments, we're getting significantly larger isotope fractionations. And this surprised us. It surprised us in many ways. Okay, so as I said before, if we calculated the equilibrium isotope fractionations as a function of temperature, we'll get fractionations that evolve to 0. Okay, so we get less of a fractionation effect. And on this narrow temperature range, it's not so steep. Instead, we get larger fractionations than what's predicted by the equilibrium effect. So we're actually amplifying an equilibrium value. The amplification is larger for higher temperatures, and so we're actually, it looks like we're evolving away from the equilibrium behavior. So I showed you some results for iron without temperature. I showed you some results for zinc with temperature effects. We see the same exact phenomena in every system that we have looked at. I shouldn't say same exact, same qualitative phenomena. We see large isotope fractionations compared with equilibrium. We see them evolving as we change the rate. And we see temperature effects that always seem to go as we increase temperature, we increase the fractionation factors. So here we see our iron chloride results now with increasing temperature. Lithium deposition, and this lithium system was chosen especially because we were concerned about mass transport. And we know that lithium diffuses relatively quickly compared with iron and zinc in solution, and that maybe we would bypass any stagnant layer effect. But we saw the same thing. We see the same type of thing in the copper sulfate copper system, a little more complicated because the solution species is complicated in the copper system, but we get the same basic types of results. So every system that we look at, we see that same temperature effect. Okay. Our next observation has to do with yes?
It looks like there's a little dip from the 50-degree one in like almost all of your systems. Is that?
Oh, interesting. Let me keep your eye on that one. We'll see some of this data later. Let's see what it looks like. That's interesting, right? It does look like that. I never noticed that. Thank you. Okay, so the next observation has to do with mass transport to the electrode. So the result that we see is that the better we mix the sample environment, or the better that we mix our fluid in the reservoir, the larger the fractionations that we observe. This is the opposite of what you might think if there was a stagnant layer across which diffusion was controlling the isotope fractionation. So the faster that we mix, the larger the fractionations that we observe. We can do that by mixing mechanically with a mixer at the bottom of the potentiostat. But a cleaner way to do it, in a way that's been developed in the electrochemistry community, is by using a rotating disc electrode. So the electrode is actually at the bottom of a cylinder, almost identical in size and aspect ratio as this laser pointer, and it now rotates about this axis. The faster it rotates, and then the electrode is at the bottom, the faster it rotates, the more material is pulled up hydrodynamically to the bottom. And so you can run a series of experiments under controlled fluid support to that electrode. And so we know that the flux of material going through the electrode as a function of rotation rate. So now not only are we just mixing, but we're mixing in a very precise way. So if we do a series of experiments now at relatively large driving forces, the faster that we rotate, that is, the more material that we're supplying to our electrode, the larger the fractionations that we see. We decrease the driving force, remember, so we're slowing down the reaction, we see the same effect. If we decrease the driving force even more so that we're relatively much closer to equilibrium now, this is where we usually see our largest fractionation factors, our fractionation is no longer a function of rotation rate. And in this case, we think, and this is all at one constant driving force, so it's at a constant rate. It's no longer a function of rotation rate. So we feel like in this case, we've hit a limit where mass transport is no longer one of the controlling factors in the experiment, and that we are actually measuring an electrochemical rate here. Maybe this is what's happening in those high temperature experiments, going back to your question, that we're at this limit already where mass transport doesn't matter. Okay, so now we have a series of measurements that we can make as a function of rotation rate, which is also telling us something about the diffusion limited rate of our reaction. So we can plot now our measured isotope fractionation. Now this is for that data that we just saw. This is iron deposited from iron sulfate and iron chloride. Instead of showing the rotation rate, what I'm plotting here on the x-axis is a dimensionless parameter that compares the current at which the experiment was run, or the rate that the experiment was run, to that mass transport, that diffusion limited rate. In which case, all of the data fall on a nice, clean line, linear relationship, over several orders of magnitude. So this is nice. So all of that data collapses to one. So our conclusion is that the isotope fractionation that we see is dependent on both temperature and rotation rate, and that demonstrates that we have competing kinetic controls on this isotope fractionation, that we're actually able to tease out the relative effects of those controls. So here we ran a series of experiments combining the controlled hydrodynamics, or the controlled transport, with temperature. You can see when we run these experiments with a rotating disc electrode, we reproduce what we expect with this. As you increase temperature, you get fractionation factors that are closer to equilibrium. So as you decrease temperature, you get larger fractionation factors. So here's a table of many different experiments, different potentials, different temperatures, different rotation rates, and we can do the same type of calculation and plot all of this data on our dimensionless plot, and everything scales nicely. Okay? So all of the temperature effect is related, because as we increase temperature, we're increasing the mechanisms, right? Our flow mechanisms, our diffusion through the fluid. Since we're increasing that temperature, that effect beats out the other effects. So all of the temperature and all of the rotation rate fall on this one axis. Okay, so conclusion, the question that we originally asked, does electrochemistry do redox processes generate specific geochemical signatures? And the answer is yes, electrochemical fractionation does. It's large, it's tunable, we know how to control it. So you tell me what fractionation factor that you might want to imprint in iron, and I could brand a nice piece of iron metal for you with electrochemical isotopes. And it's ubiquitous. Every system that we look at, we see the same type of behavior. It's also predictable, which I don't have a chance to show in this talk, but it's something that I'm working on this summer. So I think I will stop here to take any questions, because the next steps will be to show you some of the theory and then where we're going with our next set of experiments. Thank you. Yes?
What would be the relation between, I guess, what you call the overpotential and something like a redox buffer that we might think about in the mantle? In other words, how can you apply these sorts of things to?
That's right. Great question. So the relationship is direct. So if you have a buffer system, what a buffer is by definition is you have a large reservoir of an oxidized reservoir in contact with a large reduced reservoir. And the transport between those two reservoirs is fast compared to everything else, so that it's always at redox equilibrium, okay? So you have a large reduced reservoir, a large oxidized reservoir, and if you add something that's a little more reduced, that reservoir will move to accommodate that in a quick way, quicker than you're adding material. We can quantify the free energy of that system, and we can write an electrochemical potential. A voltage is equal to the number of electrons transferred going back and forth times Faraday's constant. Well, I guess the free energy is equal to the number of electrons involved in that redox buffer times Faraday's constant times the voltage. So that's the relationship between your thermodynamic free energies and your voltages. Now, how fast it goes back and forth, that's kinetics, and that's more complicated. But the relationship is direct. If one of the reservoirs is oxygen, you can calculate an effective oxygen activity as part of the thermodynamic calculation. We call that an oxygen fugacity. And so you can map free energy, voltage, oxygen fugacity thermodynamically. And that's been laid out in several places. Yes?
Good question. I should have the microphones passed. What's the difference between electrochemistry and plain old chemistry? I was told once upon a time that chemistry is electron transfer. Isn't that what electrochemistry is?
It is. Electrochemistry is electron transfer when the electron transfer is the rate limiting step. I think it's a narrower view of electrochemistry, and that's the way I learned it. So in chemistry, where any chemical reaction in detail, of course, is a movement of electron distribution from one physical place to another, in a chemical reaction, that rate limiting step is not that movement of the electron. So that's a result of usually mechanical movements. In electrochemistry, that electron transfer is the rate limiting step. So if you have a reduced reactant and an oxidized product, you can drive it forward by supplying electrons. So when electrons are participating chemical species, it's electrochemistry. That's my working definition.
Well, then to follow up, wouldn't we expect the physical transport of atoms to be rate limiting in most of the Earth rather than getting those electrons around?
That's right. For electrochemistry to be interesting in the Earth, the electrochemistry has to be the rate limiting step, or else it's just a diffusion problem. Absolutely. Which is why in the Earth, electrochemistry, and actually in all electrochemical processes, wherever electrochemistry is interesting, in corrosion in the Earth at the core mantle boundary, is at interfaces. And usually at interfaces where there's at least one fluid phase, so that something can do the transporting really quickly. So solid electrochemistry, tough to do. Yeah. Good point. Yes? Yes, a metallic phase. That's right, because a metallic phase is fluid for the electrons. Thank you. Good. Good. Yes, but if you were to suck, if you were to reduce something oxidized in the mantle, you would be limited by mass transport in the mantle to the core mantle boundary. And that was one of the issues that I ran into looking at that problem. Yes?
John talked about the mass difference, for example, between the different isotopes as a function as well as temperature. When you were looking at the different mass fractionations with changing temperature, for example, recognizing that they're different solutions,
Yes.
can you predict the magnitude of the isotope fractionation based on the mass difference between those isotopes between systems?
Great question. So now, of course, you're starting to ask questions about the theory, which are kind of near and dear to my heart right now. The answer is no. Okay, so the prediction, and Anat showed this, the prediction for kinetic reactions that a kinetic isotope fractionation, this is based on ideal gas theory, is going to be related to the square root of the ratio of the masses. Okay, and that's very, very, very large compared with what we see in these condensed matter, liquid and solid systems. So we always see kinetic isotope fractionations that are lower than this prediction from ideal gas theory or from transition state theory too. So the question is how much lower? And so, an empirical view would be it's, the square root of the ratio of the masses minus some parameter that is to be determined experimentally. I have these three plotted here. Unfortunately, I did not normalize them to what would be expected for their mass. But lithium is really, really light. Okay, but the maximum fractionation that we observe is 3%, which seems like a lot when we compare it to the iron, and zinc, few part per thousand. But actually, this is a lot lower when you compare it to the actual mass ratio. And so what we're seeing in the lithium experiments is actually close to what's predicted for the equilibrium fractionation factors between the product and the reactant phases. So when we actually scale for that mass effect, we see much less of effect when we look at lithium. And for iron and zinc, we always see larger fractionation factors in the zinc, which is heavier than the iron. So we're reversing here. So there's something about that zinc system where electrochemistry, either the speciation is much simpler, or for some reason the electrochemistry is really dialing it in. Zinc especially is an interesting one. Zinc isotopes are really important because zinc is a corrosion inhibitor to be used in heavy water nuclear power plants. And if it's a heavy water nuclear power plant, then you want the isotope of zinc that has a much smaller neutron scattering cross-section. And so there have been large facilities that have been using actually mercury amalgamation. So it's a zinc reduction reaction with a giant mercury bath to separate zinc isotopes. And that's left large environmental messes. So here's a technique that you can use. We get much larger single pass fractionation factors. It's a lot cleaner. I haven't done the engineering calculations to see if it's more energy efficient. But there are practical applications to these isotope separations, which is another reason that we need the theory, right? So we can ask, well, how high can we get those factors? If we were to design a really good experiment, could we do even larger ones?